Good afternoon, everyone. I'm Qingchang Han from Beihang University. Today, I will introduce our work, Extremely Low-Bit Convolution Optimization for Quantized Neural Network on Model Computer Architectures. The presentation is organized as 4 sections. Firstly, I will introduce the background, and then I will present our optimization methods on ARM CPU and NVIDIA GPU. After that, I will show the experimental results. Finally, I will make a conclusion. I will begin with background and motivation. Convolutional neural networks have been successfully adopted in many fields, such as computer vision, automatic driving, speech recognition, and recommender system. Here is a classical CNN architecture, including convolution, pooling, and full connection layers. With the increasing demand for higher accuracy, the number of layers and parameters has been increasing, which requires more and more computation resources and memory footprint. So researchers have been trying to optimize the computation complexity and memory footprint of CNNs. Furthermore, the previous works show that convolution layers dominate the computation and inference time of CNNs, so convolution is the focus of our optimization. Several model compression methods have been proposed to reduce computation complexity with acceptable accuracy, such as network pruning and model quantization. Network pruning is a method to get a lightweight network by removing the least important part in the heavy network. Model quantization method converts float data to low-bit data to reduce model size. Here we focus on model quantization. Model quantization takes advantage of the insensitivity of DNN to data precision and maps data to a smaller size of numerical representation, which can improve the speed and reduce memory footprint while preserving accuracy. As shown on the right, we introduce the uniform symmetric quantization. The quantization converts float 32 to int 8, which divides the scale into x float and execute round and clip operations and get x quantized. In contrast, the dequantization converts int 8 back to float 32 by multiplying it by scale. Below is an example of int 8 convolution quantization. First, quantize the input and weight in float point to x quantized and w quantized, and use them to calculate the low-bit convolution and get y quantized. Finally, we dequantize it to y float. So for convolution quantization, we need to focus on optimize low-bit convolution. Recent works have proved the accuracy of quantized neural network. The figure shows the accuracy comparison of low-bit QNNs on ImageNet. We can see 8-bit quantized models can almost reach the same accuracy as the full precision one. Lower-bit quantized models only lost accuracy slightly compared to the full precision ones. Although the state-of-art quantization algorithms can obtain good accuracy, achieving the optimal performance of QNNs across different computer architectures is challenging and less studied in literatures. Many factors will affect its performance, such as convolution method, data layout, low-bit instructions, and memory size. For inference of convolutional neural network, there are many computer architectures, where the most widely used platforms are ARM CPU for edge devices and NVIDIA GPU for cloud accelerators. These architectures provide native support for low-bit arithmetic instructions. For example, there are MLA and SMLAL instructions on ARM CPU, and there are TP4A and MMA instructions on NVIDIA GPU. So we focus on low-bit convolution optimization on ARM CPU and NVIDIA GPU. Convolution layers use many multiply accumulate operations. For ARM v8.1 architecture, the existing low-bit multiply accumulate instructions are 8-bit SMLAL and MLA instructions. These two instructions both take in 8-bit input data, but generate 16-bit and 8-bit output, respectively. And the SADDW instructions can accumulate low-bit data to higher-bit data. NVIDIA Volta and Turing architectures introduce tensor cores, which can natively support mixed precision GEMM. For example, Turing tensor cores support 1-bit, 4-bit, and 8-bit GEMM. Tensor cores can provide powerful inference performance. For example, RTX 2080 Ti delivers up to 215.2 TOPS of int8 inference performance. Developers can use tensor core in 3 ways: CUDA WMA API, MMA instructions, and some vendor libraries. MMA instructions support more flexible sizes for matrix multiplication and enable programmers to manage registers explicit. Therefore, we choose to use MMA instructions to utilize tensor core. Let's see current low-bit convolution support in existing frameworks and libraries. On ARM CPU, NCN, QNPAC, and TF-Lite only support 8-bit convolution. TVM supports 1-bit and 2-bit convolution. On NVIDIA GPU, CUDA and TensorRT supports 8-bit convolution with DP4A instruction and with tensor core, respectively. Quantized only supports low-bit GEMM with tensor core. It does not intuitively transform to efficient low-bit convolution implementation. Therefore, to the best of our knowledge, there is no public framework or library that can support extremely low-bit convolution covering a wide range of bit widths on ARM CPU and NVIDIA GPU. The missing support for extremely low-bit convolution motivates us to provide efficient implementations on ARM CPU and NVIDIA GPU. Next, I will present our optimization methods on ARM CPU and NVIDIA GPU. On ARM CPU, we transform convolution to GEMM by image-to-column method. The load instructions are much slower than arithmetic instructions, so we redesign the GEMM microkernel to improve the arithmetic intensity of GEMM-based convolution. In the microkernel, the dimensions of matrices are really small. Here we assume that matrix A, B, and C are all 3x3 matrices. We allocate buffer A, B, and C in registers. There are 4 steps in our GEMM kernel. Step 1, load 1 column of matrix A into buffer A. Step 2, load 1 row of matrix B into buffer B and replicate it into each row. Step 3, perform element-wise multiplication between buffer A and each column vector of buffer B and store the results to buffer C. Step 4, after all the calculations are done, copy the data of buffer C into matrix C. We also apply data padding and packing optimization for better performance. Here assume that the dimensions of matrix A and B are 3x4 and 4x3 respectively. The dimensions of submatrix A and B in the microkernel are both 4x4. Here the dimensions of the matrix is not a multiple of the required dimension, so we first perform zero padding for both matrix A and B, and we pack and transpose on matrix A and pack on matrix B for continuous data access. We propose 2 instruction schemes for optimizing low-bit GEMM. For 4 to 8-bit GEMM, we choose SM, LAL, and 16-bit SADDW instructions. We load the input data to 8-bit registers. Then the SM, LAL instructions perform multiply accumulate operations and output to the 16-bit registers. This process continues until the 16-bit registers saturate. Then the SADDW instructions accumulate the data to the 32-bit registers. For 2 to 3-bit GEMM, we choose MLA and both 8-bit and 16-bit SADDW instructions. We also load the input data to 8-bit registers, and the difference is the output of MLA instructions is 8-bit data, so we need to use both 8-bit and 16-bit SADW instructions to accumulate the data to the final 32-bit registers. We also propose register allocation optimization to accommodate different instruction schemes for low-bit GEMM. We allocate registers for buffer A, B, C, and temporary results. For 4 to 8-bit input data, we only need to store 16-bit temporary results. Here, we group registers of buffer A and B and use double buffer method for data prefetching. For 2 to 3-bit input data, we need to store temporary results in both 8-bit and 16-bit. This occupies more registers. In addition, the throughput of MLA instruction is twice that of SMLAL instruction, so we simplify the register allocation. We also apply Winograd Optimization to 4 to 6-bit convolution on ARM. Due to the time limit, we don't introduce it now. For more details, please refer to our paper. We use implicit precompute GEMM method on GPU. The traditional explicit image-to-column method performs global matrix transformation, but the implicit GEMM method performs the local conversion in each thread block, reducing memory footprint. Furthermore, we use a precomputed buffer to store the offsets of elements of a matrix A, which can reduce the overhead of computing index. For a specific shape, the offset calculations only need to be done once and can be regarded as the pre-processing of the kernel. Next, we propose a data partition mechanism along with thread hierarchy on GPU, which partitions the matrices at grid level, block level, and warp level. At the grid level, we divide the matrix A, B, C into tiles with parameters M tile, N tile, and K tile, and assign each C tile to one thread block. Here, A tile and B tile can be reused by warps, so we store them on shared memory and directly store C tile on registers. At the block level, block row warp number and block column warp number means the number of warp rows and warp columns in each thread block. We partition the submatrix C tile into fragments based on these parameters. To avoid the value of K tile is too large, we use the factor K step to split K tile loop and also partition A tile and B tile into fragments. Here we store all fragments on registers. At the warp level, each warp contains a call by MMA instructions to perform the matrix multiplication. The above process involves many tiling parameters, such as M tile, N tile, and K tile. To support auto-tuning of parameters, we use C++ template to generate multiple kernels with different combinations of parameters, and choose the best one through profile runs. The optimal parameters only need to be determined once per shape with negligible overhead. We propose multi-level memory access optimizations. We implement coalesced access on global memory. For example, we use each thread to access consecutive 16 bytes, so the whole request in one warp is divided into 4 independent memory requests for 4 quarter warpers. In addition, we use built-in vector types in CUDA, such as int4, to implement automatic alignment and coalesced access. We also use read-only cache with LDJ function to improve performance. We also reorder the access pattern of matrix A and B on shared memory to increase continuous data access of each thread. The common method is that each thread performs thread memory access with 4 4-byte data blocks, as shown in Figure A. In Figure B, we reorder the computation and memory access of matrix, reducing the number of load instructions. We utilize registers to overlap MMA calculation and global memory access. Specifically, we set up a temporary buffer on registers to prefetch the data required for the next iteration. At the beginning of each iteration, the data in this iteration is already in the buffer, so we can load the data directly from the buffer to shared memory. Then the processes 1 and 4 can be performed simultaneously for overlapping computation and memory access. We also perform the in-place calculation of bias and requantization on registers, instead of writing the data back to global memory first. We exploit two ways of layer fusion in quantized neural network. Due to time limit, we don't introduce them now. For more details, please refer to our paper. Next, I will show the experimental results. This table shows the hardware and software configurations. We choose Raspberry Pi 3B and NVIDIA RTX 2080 Ti. We evaluate ResNet 50 and DenseNet 121. Here, due to the time limit, we only introduce results on ResNet 50. On ARM, we choose the NCN and the baseline. On NVIDIA GPU, we choose the CUDN and the baseline. This figure shows the performance comparison of our kernels and NCN on ARM. The x-axis indicates the different convolution layers, and the y-axis shows the speed up compared to the baseline. We can see that the performance of our optimized 2 to 7-bit convolution kernels exceeds NCN in most layers for ResNet 50. Although our instruction schemes performs less well than NCN and 8-bit, they are more efficient when applied to lower bit convolution. This figure shows the performance comparison of 2-bit convolution between our kernels and TVM. Our 2-bit implementation outperforms TVM in most cases, with the highest speedup of 2.11 times, and the average speedup of 1.78 times. This figure shows the performance comparison on GPU. We can see that with a batch size of 1, our 4-bit and 8-bit convolution kernels outperform TensorRT in most cases, with an average speedup of 1.78 times and 1.44 times, respectively. With a batch size of 16, our 4-bit kernels also outperform TensorRT in 12 layers by an average speedup of 1.46 times. The experimental results show that our implementation achieves better speedup with small batch size, and our optimizations are more effective towards lower bit convolution. This figure shows the performance improvement after using profile runs. The average speedup of 4-bit and 8-bit convolution kernels with the profile runs enabled is 2.29 times and 2.91 times, respectively. Let's discuss the space overhead. On GPU, only the pre-computed buffer occupies negligible global memory space. On ARM CPU, this figure shows the space occupation of image-to-column and data padding and packing. The baseline is space occupation of input and weight for each layer. We can see that the overhead of image-to-column for some layers is relatively high, for example, Convolution 2 and Convolution 6. The overhead of image-to-column is determined by kernel size, stride, and input size, and the overhead of data padding and packing is determined by the size of image-to-column matrix and weight. Finally, I will make a conclusion. In this paper, we explore extremely low-bit convolution optimizations and provide efficient implementations on ARM CPU and NVIDIA GPU. On ARM, we redesign GEMM computation and propose instruction and registers allocation optimization, and we also propose Winograd optimization. On GPU, we propose data partition along with thread hierarchy. We also propose multi-level memory access optimization and exploit layer fusion. Experimental results show that our kernels get significant speedups compared to the existing frameworks and libraries. That's all. Thanks.